I think it's time to start. So Joe, thank you very much today. And Joe is will talk about building an interpreter in RPython.
Hello, test. So this talk is about RPython, and the slide is waiting because it takes so long. It uses the extra cycle. That's why. So, my name is Joe. I live in New York. I also travel a lot and I speak a lot of different events. And I'm a huge fan of Japan. So yay. This is in somewhere upstate New York. It was very cold. So before we go and talk about interpreters, before we go and talk about RPython, I thought it would be a good idea to introduce what interpreters are in the first place, and then we can dive in what RPython is. So interpreter is a very, very simple program. It does primarily three things. First of all, parses your source code. So it takes a bunch of files, parses some kind of internal structure. Then generates bytecode and executes that bytecode. Most of the interpreters also have a standard library. So instead of only having execution, it comes with some functionality. Usually it's I/O. Different languages have different standard libraries. So for example, Smalltalk interpreter only has a very small amount of features. Python interpreter has a lot of standard library features. So the first two steps can be looked at like this. So first of all, what we're doing is we're relaxing the program. And all that is just turning a string, which is your source code file, into a bunch of tokens, all you do is just split by space. Then you construct an abstract source tree. So instead of looking at it as a source file as just a list of tokens, you construct a source tree. This is very useful to run all sorts of analysis and static analysis on your source code, do transformations on your source code, all sorts of different things. Once you have an AST in hand, then you can create a bytecode. We're going to look at it, what it actually is, but it kind of is like a machine code. And once you have bytecode, you just run through every single command in a loop. Done, your program runs. So how it actually all looks like. So imagine you have a simple Python function. You can actually look at the bytecode of that function using the this module, comes as part of Python. And if you ran it, that's the result you will get. A few of these pieces like this is kind of like comments. And the first numbers there are also kind of comments. They're not actually part of bytecode. The middle part is part of bytecode. And it's pretty obvious what it does. And it kind of looks like assembler in some way. All you have is a bunch of function calls and a bunch of arguments. So for example, the second line of our function is a equals 2. So this line does load constant 1, and the first constant is the number 2. And then store fast means take whatever is loaded and store it in a variable. And we do it twice. And then to sum those numbers up, we load them back into the stack. We do a binary add, and then we return a value. This is in a nutshell what bytecode is, and that's all you have to generate to be able to run programs. In your Python folder, you would usually have PyC files. They're storing this in a binary format. Because as long as your source code doesn't change, so you're not modifying it, this will also doesn't change. So you can cache the results. The interesting part of execution, though, is that for all of these, you have to call some kind of a machine level function. So if I had a print statement, someone has to print to the standard out. To help with execution and to make it faster, most interpreters now have JIT. What does JIT mean? Well, with JIT, instead of instead of calling machine functions for every single bytecode, we're actually we're still doing that, but we're also recording what happens. And if we think we can optimize that, we stop the execution, we generate machine code, and then we continue the execution. For how it works. Imagine you have an if statement in your source code, and always your program only uses the true branch. With JIT, it will actually realize that the else branch never gets called, so it doesn't even have to check. It doesn't even have to run the if statement. It can just keep executing the true branch, and it will thus generate a machine code which only does that. JIT is a very complicated piece of source code, and in interpreters, that's usually the most complicated piece of source code. But what it allows you to do is to write kind of higher level code, Python code, and use JIT to generate machine level code on execution. As long as your program runs for long enough, so maybe it's a kind of web server or some kind of a long running program, JIT interpreters using JIT will probably be as fast as anything you would write in C code. So where does RPython come in all this picture? Well, the problem is writing interpreters is really, really complicated. Writing JIT compilers is even more complicated. So kind of inspired by limitations of CPython, a few people looked at ways on making Python faster. And to make Python faster, you obviously have to build it as a separate competing interpreter. So they built PiPy. And actually, PiPy is built on RPython. RPython would not exist without PiPy. So RPython. So first of all, RPython is a programming language. It looks like Python, and you can actually run it as Python, but it has removed a bunch of functionality from the language itself. Second of all, it's a subset of libraries, so it has tools to generating interpreters, to generating parsers, to generating bytecode compilers. It's ideal for writing interpreters. You can actually use RPython to write very, very fast code, and some people have tried it, but it's not actually meant for that. You're supposed to be using it for writing interpreters. It has JIT and garbage collection as part of it. So when you're writing your interpreter, you don't have to think about JIT. You can just add a few flags, and all of a sudden your interpreter uses JIT. And the final result, you can translate it to C. That C gets compiled, and you have machine-level performance without having written a single line of C code. So when it comes to PiPy, this is roughly how it looks like. The top parts are something people have written by hand. Everything in the middle is being translated on the fly, and these are the final results you get. So the way it works is it looks at this Python-looking source code. It figures out a flow graph. It means what functions are calling what functions. It figures out types, so it knows if a function is getting called by integers. And then it uses all of this information to generate C code or LLVM code or anything you want. And then you can compile the final result and have a super fast thing. And the selling point of it is that when you have RPython code compiled, it's probably as fast as anything you would write with C, but you don't have to write with C. So with 20% of effort, you can get 80% of performance, which is a really big deal. And much more importantly for us is that it's still Python code. So you can test it like a normal Python program without having to dive into low-level things. So a very important part of RPython is the type system. This code isn't valid RPython code, but it is valid Python code. Why? Because you have the same variable being assigned two different types. Most like low-level languages like C would never allow you to do this. RPython doesn't allow you to do this because this is very slow. This is very slow for the reason being that anytime you want to use X, it wouldn't know what type it is because it can be either of those. And that's why in RPython, a variable is of a single type. It does a lot of clever things where again, because it's analyzing the flow graphs, it knows that there's a chance that x can be none or an integer. It's incompatible. So this line will not compile. It will say, hey, by the way, x could be either of those, and in one condition, you can't add none to numbers, and it will fail. To help with that, of course, you use inheritance a lot. So because you can't have a single variable use different types, you could have a single variable have two different subclasses. But when it comes to, for example, calling child and this attribute only exists in one child, and our children might not have it. So you would use assert statements to being like, hey, RPython, like I've written this code, and I know that anytime I'm calling this method, I will only pass children A. So just trust me, it's that. So across your code, you would use asserts a lot. And when it comes to JIT, a big part of JIT is understanding what changed and what doesn't change, because what doesn't change, you can optimize. So you can add the hints to pretty much any class you write, where you're saying, hey, these fields never change. So my bytecode, whatever variable type it is, and my arguments list never changes. So if you want to store it somewhere safe, do it. Another hint you would use for JIT specifically is that, again, if you know that this class, the variables inside of it will never actually change, like in this list, anytime you're calling it with a name, the result will always be the same. So it's a deterministic function. You can actually hint it to JIT saying, hey, the moment you get a single result, this will always be the same. And you might be asking, like, how is this useful? This looks just some kind of just caching. It's super useful because in interpreters, what you do the most is being like, hey, I have a variable named A, where I should store it. What's the index for memory for that? If I have a variable named var, where should I store it? Most of the time you're doing dictionary lookups, and dictionary lookups should be cached. So how do you actually work with RPython? You write valid Python, and then you hope it works. And it never works. So still, like the best way to do is you write valid Python and you test it with just normal testing tools. And then you modify it until it becomes RPython. Most of the time, there aren't any like very strange edge cases. The difficult parts is the type system. So if you have a complicated program where variables get passed around a lot, and you don't really know if you're sticking to the same variable type, or you have some kind of dictionary and your dictionary gets different types of variables, different types of classes stored inside of it, it will never allow you, and sometimes it is pretty difficult to figure it out. But luckily it does have some pretty good debug tools, so it will usually tell you, hey, I tried to compile this block of code, it didn't work. So how do you start any of this? It's actually pretty simple. The shortest program you can write looks like this. All you have to do is have a target method, which then RPython will call on compilation time, just to figure out the entry point, and thus your entry point is the main function. The entry point will get called anytime you run your compiled program. So how do you write a simple entry point? And this is going to be the most basic interpreter you can write. Entry point, again, just gets normal arguments passed to it, so you can do anything you want with it, and all this is just normal Python. So all I'm doing is saying, hey, let's read the file. All it returns is just a string. Once I have a string, I'm going to process that in an AST tree, like we talked about, the tree structure of my source code. Once I have the source tree, I want to compile it to bytecode. And once I have bytecode, I have some kind of an interpreter implementation which is able to run the bytecode. So let's look at all these steps and how they actually look like. So first of all, parsing. Parsing, as it turns out to be, is the easiest part. Because all you have to do is create a grammar, which most of the time you're creating it into some kind of a text form. And And then you can use RPython tools to generate parsers for you. So you see what I'm doing here is loading up a grammar file, and then everything here is just RPython functionality. It knows how to parse the grammar text file. It knows how to create a parser, and then I create this helper method, which encapsulates all of that functionality. And I will show you how a grammar file looks like just in a second. Once I have a parsed source file, let's create an AST tree. This gets interesting, and the easiest way to do that is to use a visitor pattern. Again, I have a helper function where it gets a parsed source tree, and then I'm using an RPython transformer from here, which for every type of a node I have, so for example, if I have an if statement, I'm recursively parsing it and creating instances of operations. So the result of this transformation stage will be a tree structure of these operations. And I'm running quickly through this because I'll share the slides later, so you can always analyze the source code. And once I have parsed to AST, all I have to do is for every single type of a node, call compile on it. So let's say I have a print node, so my AST tree contains a print node. Well, obviously the print node encapsulates something. You're always printing something. So print will have usually a variable or a function call. So the first thing I'm doing is calling its print, so it's a recursive function. And then I'm omitting print bytecode. So the end result of this, again, recursive bytecode generation will be the same list I've showed before, just a bunch of omitted bytecodes with their own arguments. And then there's the final step, interpreter. So this piece of code is actually what an interpreter by definition is. In CPython, it's probably 10,000 lines of code. Luckily for us, in RPython, it's just this. And if you actually just pay attention to it, it's extremely obvious how it works, and it's extremely obvious what it does. First of all, I'm creating a frame, so a place to keep variables. Most of interpreters uses a stack structure, so you can load variables on top of it, and then pop the variables from the top. Just a bunch of checks. If I don't have any opcodes to run, opcode count 0, don't do anything. And then all I'm doing here is creating a position variable, saying 0. Get me whatever is at 0 position, so the first bytecode in a list. Evaluate it. Maybe the result was a jump. So if you have if statements or you have loops, they would usually use jumps, which means jump back. If it's not, just keep executing until the next one. And maybe the opcode is a return statement. So whatever is currently on top of a stack, just return the variable back to us. That's all it takes. And in a simple form, that's all what an interpreter is. It's just a loop for a list of bytecodes and just delegating the functionality to them. So of course, if in my print bytecode, this eval function would implement a print, which would mean print something to standard in and out. In our case, again, it would be in Python. That's all there is. And luckily for us with RPython, we can take this piece of code and make it super quick by adding JIT. And all it involves, and I haven't changed anything. All I did is just kind of shorten the source code. All I'm saying, hey, I have a JIT driver. And a JIT driver, all it has to know is where every single step starts. And if at any time and at any point we're jumping backwards, you also have to tell the bytecode interpreter that. That's it. And because of the way a JIT interpreter works at runtime, it will know that it can trace the path until the point we're jumping backwards. And if we're jumping backwards, it probably can't do it much more. That's it. Like adding this will make your code 10 times faster. And once I've written all of this, and I've wrapped it in some kind of a Python file, I can go ahead and compile it. So you run Python RPython, and you compile it. I would recommend trying first without 0 optimizations. Optimizations tend to break your code, so just try it first without any optimizations. And the end result will be this big binary blob, and then you can run it as a normal program. It's going to be pretty big, but it's going to contain everything it needs. And if it's fast enough for you now, you can go ahead and try adding JIT. And all you have to do is do this. Instead of doing O0, which means 0 optimizations, do O equals JIT. This will take much longer because it has to figure out more about your code. It has to figure out more about your paths. But the end result is going to be the super, super quick JIT-enabled interpreter. The problem with JIT, though, is sometimes it could be hard to optimize that because, as I was saying, like JIT works on runtime. So it's optimizing your code on runtime. So how do you know it's doing the right thing? Well, luckily, with RPython, you can debug all of it. So instead of running your program just like before, I'm also defining this environment variable called PiHP and it will output all the decisions it makes at runtime. So you can take your program, maybe run it with some kind of a bench file you've written, and look at what PiHP says. And it will tell you anytime it makes assumptions about variables, and anytime it loads a variable, unloads a variable to a stack on the actual OS level. Super useful. You can also show it as a graph. Again, once you have generated the JIT log file, you can generate a graph out of it. Again, visually look how it actually works. So I've used all of this to write my own interpreter. One of the craziest and pointless things I've ever done. So what I've written is called PiHP. And as the name suggests, it is a PHP implementation in Python. And it's not a joke, it's a real thing, it actually works. So what it actually involves? So first of all, of course it implements the basic PHP functionality. A big thing I learned about writing interpreters, you spend most of your time implementing language features. So I chose a short list of just the most basic features, so defining variables, defining functions, calling functions, implementing loops, et cetera, et cetera, et cetera. I've also added a bunch of debug tools and an HTTP server. And because it's written in Python, it also has a bunch of Python tests, which if you looked at how CPython is implemented and how CPython works, testing it is so much more difficult. But because all of this code is just Python, I have a bunch of tests, and I will show you how they actually work. And thanks to JIT, it's also super fast. And I kind of started, first of all, I found this first a very simple Lisp interpreter, and I just changed it until I got it to work to PHP. And then, of course, it involved more and more things. So when I was talking about grammar files, this is what you would use to define languages. There are different kind of domain languages for defining programming languages. EBNF is probably the most common one. Even when I was studying in the university, that's the one we kind of learned. And what it allows you to do is define tokens. So the first line is a token saying, okay, in PHP, a variable name starts with a $sign and then a bunch of characters. And then defining expressions. So for example, if I have an if statement, again, it starts with an if. You have some kind of a comparison expression. Then there is a true statement, else, an else statement. Or maybe there is no else statement, so it just looks like this. And my statement could be a block of code, could be an assignment operation, could be an if statement, etc. That's it. And the whole PHP language is defined as this. And you can use it for defining Ruby languages or any languages you want. And then RPython generates the actual parser. So if I want to add any features, if I want to change, add some kind of maybe assignment operation, I don't really have to change a lot of code. I just use our grammar file, it works. Because RPython doesn't allow you to store mixed types in a single variable. It also doesn't allow you to sort mixed types in a list, because again, it's very hard to optimize. So you implement your variables as these kind of boxed objects. So for example, if I have a Boolean object, and all it does, it stores the Boolean actual value inside of it, and I can like create a string from it. I can check it if it's true or not. But my frame in execution time will have a bunch of instances of w_root, and then the interpreter it just knows that it's always going to be w_root, not just a bunch of random simple types like Boolean values. So when I was talking about tests, this is what I did. Like, it's not pure unit tests, but you could actually do that. But all I did was have small snippets of PHP code, and I would call the actual interpreter loop with them and check the output to match whatever I was doing. So before I started this whole PiHP thing, I defined maybe 100 or so tests of just the most basic functionality, from assigning variables and printing them, to doing if statements, to calling functions, and to using like some specific PHP functionality, like using references. And then I just kept testing my code until it worked, and eventually it did. If you want to try it, and I recommend trying it, it's pretty fun. I've used Docker, so I've packaged up all the RPython and PyPy source code in a Docker container. So you can pull a Docker container, you can build PiHP, and then the first fun thing you can try is running the bench file. So PHP comes with a bench script, and it's roughly 15 language level benchmarks. So calling a function 1,000,000 times, calling a loop 1,000,000 times, all these different things. And it tests how quickly a language interpreter works. So PHP 7, which is the latest version of PHP, the output of it would look something like that. So it takes 1.1 second on my laptop, which is like a couple-year-old MacBook. PiHP takes 0.3 seconds. And it's kind of insane, but and it's so quick because it has JIT. So benching in general is the best use case for JIT, because if you're calling a function 1,000,000 times, by the time it's like 1,000th call, I can generate optimized machine code, which I don't have to do. RPython does it for me. I don't have to do it. So it generates basically machine code for all of these functions on runtime, and the end result is this crazy performance difference. Of course, it doesn't have the full features. Of course, it doesn't have the full standard library, but it just shows you the potential of using a higher level toolkit like RPython without drilling down to C code, without drilling down to assembler code, and getting an interpreter which is much faster than a handwritten C interpreter. Makes you think about how to write things. A very good feature of having written this in Python as well is that on like the initial user group meeting I've given this like a while ago, someone was like, oh, PHP doesn't support Unicode. So in PHP, strings are binary strings. They're not actually Unicode strings. And someone was like, oh, if you're using Python, which of course has Unicode strings, why can't you make your PHP compiler also use Unicode strings? So it's like, okay, that looks very interesting. So it took me, all I had to do is change 280 lines, and my interpreter became a Unicode interpreter. PHP project, just a part of history, tried to do the same thing for the actual PHP implementation. And the reason why it went from PHP 5 to PHP 7, because PHP 6 was supposed to be the Unicode PHP, which after spending 2 years or so, it didn't work. Because again, doing that, like converting C PHP to Unicode is so insanely complicated and so hard to do. It ended up failing as a project. In my little Python thing, it took me 5 minutes and I've done it. Again, shows the potential of writing things in the higher level languages. So you can think about it like anytime you want to like even play around with Python and extending Python, adding extra functionality, you could do it with PyPy in a matter of minutes. In CPython, it would take you much longer. So biggest wins. There's no C involved, no assembler involved. A fun side project you could actually play around in a weekend and write a working interpreter for any language you want, maybe for the domain language. It's very, very fast because RPython is not a toy project. It's being actually used by PyPy. So everything it does is actually real, legit things, not just jokes. The final code base is very, very small. So PiHP is maybe a couple thousand lines of code, and it runs most of the basic PHP code. And it is testable because all of it ultimately is just Python. Biggest issue. Biggest issue number one, nothing is documented. Absolutely nothing is documented. Now there are starting to appear a few documentation repositories, but basically any time you get a somewhat complicated error, you look at PyPy source code and then try to figure out why it's throwing that error. While RPython makes interpreters approachable and easier to write, it's still not a trivial operation. So while we're trying to make the errors as understandable as possible, it's still not perfect. And I don't think it's ever going to be perfect. PyPy, of course, also doesn't have a lot of funding, so they can't really afford a lot of time to write massive documentation boards. It's really fun when you get an error and you go to Google and when you search for that and then it shows 0 results found. Then you really know you're deep into something. My biggest frustration was like you write your interpreter and then it's translating, compiling it to C for 15 minutes, and after 15 minutes it throws an error saying, oh, something didn't work. And then you're like, I don't know what I changed. I don't think I changed anything. So then you have to like either revert your Git commits just to figure out what was the final base. The thing I did to solve this, I would commit very often and I pushed to GitHub very often. So I had Circle CI run integration, like actually compile it on every commit. So I wouldn't have to run it on my laptop every time. I can just keep working and then the CI would tell me if something is broken. Ultimately, lessons learned. Most of the time, you're spending or implementing standard library. So even in terms of PHP, like the basic interpreter works really quickly, but to add all the functions it has and all the types of functionality it has and all the standard library features, that's what takes a lot of time. And that's why even keeping PyPy and CPython in sync is hard because it's just anytime CPython changes, someone has to go to a PyPy and re-implement the same functionality. And that's why keeping interpreters in sync in terms of supporting the same functionality is a difficult task. PHP doesn't really have a good spec in place, so like there are ways it works. So even when I was running the bench file, I had to like implement edge case scenarios, like or like using a variable without defining it, which in PHP is a very undefined behavior. Like sometimes it throws an error warning, sometimes it doesn't throw a warning. When you're trying to re-implement your interpreter, you spend a lot of time trying to figure out all these edge cases, like how you should do things. Some PHP specific features are a nightmare. There's a lot of them. The pinnacle of all of them, there's a PHP feature called eval, which you can pass a string of valid PHP code and it will evaluate it, which means it will run it on runtime. It will parse the PHP code as it's running. I have no idea how to implement that to this day. Function calls are expensive. So the reason why most programming languages limit how deep your function call can be, so if you try to implement Fibonacci in the most trivial way, which is calling the function recursively, most interpreters would fail after like 1,000th level iteration is reached. Because anytime you call a function, it needs to build a new frame for memory because all of a sudden the scope is different. And even in the interpreter is going recursively deeper and deeper and deeper. So implementing fast function calls is a good brain teaser. Like Imagine you call the function 1,000 level deep. What is the fastest way to check if whatever variable is referring is part of a function scope, the current scope, or the global scope? It's not easy. So when you're trying to implement bench scripts, which are calling something 1,000 times, 1,000,000 times, and they're referring to some variables 1,000,000 times, how do you find those variables 1,000,000 times? How do you concatenate strings quickly? Even Python, for example, Python 3 does a much better job at concatenating strings quickly. If I try to concatenate a string 1,000,000 times in a loop, how to do it quickly? Which means how to do that without reallocating memory 1,000,000 times. Again, not easy. So what are the resources? The More PiHP blog, which is kind of a PiHP blog of blogs, is the best place to find both basics and announcements about changes. There are RPython docs being created, which primarily talk about high-level structure and the reasons why things work and how to use them for PiHP. There's a very actively and probably the best done interpreter for Ruby called Topaz. I think it was part of someone's PhD dissertation. So it's very well done, supports pretty much all of Ruby. If you want to look at serious things, Topaz is one. And if you want to look at my PiHP interpreter, it's right here. Again, it's probably the simplest one just to look at because it barely has any functionality. So it's the easiest one, I think, to understand. And there's one more thing. So in one of the first slides, in the execution graph of PiHP, I was explaining that you analyze your flow graph, you annotate types, and then you generate the output. And the thing PiHP and RPython does by default is generate C code. And then that C code gets compiled, and then you get the final executable. You can also generate LLVM code. LLVM, one of the largest kind of frameworks for writing interpreters. But you can also generate something else. And one of the things you can generate is JavaScript. Again, not entirely a joke. It's a real thing. And what it does is you can write your interpreter in Python, which then is actual RPython code, which then gets translated to C code. Then that C code gets passed to this open source project called mscripton, which outputs JavaScript. And the final result for PiHP, the final result for PiHP is like an 18 megabyte JavaScript file, which then you can take and run it with Node.js, and then pass it any PHP file you want, and it will execute that in JavaScript. And the fascinating thing about this is that I don't have to write the craziness of JavaScript generation. It all gets translated from my Python code. So like my PiHP project has not changed. I didn't add any JavaScript specific functionality. All I'm changing is the final backend, and the final result is it's not emulating PHP functionality. It's not emulating Python functionality. It's an actual VM running in JavaScript, and it has its own output buffering. It has its own memory allocation. And if you truly tried it really hard, you could run PHP scripts in a browser, and all of it is somehow magically powered by Python. Does anyone have any questions? And there might be a lot of questions. Yeah, there's a question there.
So first of all, thank you so much. I mean, I must admit I've only maybe used 1% of RPython, and I've noticed that I've completely underestimated it, so I am embarrassed. I can see my future projects all being done in RPython now. I think one of the most important questions for me, because I have tons actually, is how would you tackle static typing?
What do you mean?
Let's say, I mean, it's really easy to implement your toy example scheme interpreter and so on, but let's say you wanted to have something more statically typed, like let's say C, and you want type checking that is done at compile time, which obviously means you generate your AST and so on. Are there any facilities in RPython to do type checking already, or do you have to do that yourself when you visit the AST?
So I'm fully brainstorming, but I don't see any difference between implementing a dynamic language and a static language.
I mean,
As
for
far
example,
as
type declarations.
Right. But so like you would just have to implement the whole type system in RPython.
Yes, so the question is there a facility for that? Because, I mean, obviously you can do it while following the visitor pattern, but I was just wondering whether someone has already thought of that and it's there.
I don't think so.
Okay.
I think RPython primarily tries to focus on languages which get interpreted, not compiled. So I don't even know if there is like a RPython static language like on GitHub. I think every example I've seen were languages like PHP or Ruby or Python, which don't get compiled. But I don't see why you couldn't do it. I don't know.
So I think I'm going to do it then.
You should do it. You should definitely do it.
Thank you.
You should definitely do it. Because actually, RPython, once it's come through certain levels of translation, it in itself is a static language. But it achieves staticness through automation, not through declaration. So it figures out types by itself.
Yeah, so I was just wondering, I mean, you know, you went through all the trouble to generate the JavaScript implementation. Did you try running the benchmark file on it?
Yeah, it was like 30 times slower.
Oh.
I don't know why. To be honest.
Actually, I have read the mscriptum thing, and it is like that's kind of kind of their pitch. It's only 10 times slower than native C code,
Okay.
or only 30 times slower. So that's a pretty good result, actually.
It worked, and then I think there was like a version upgrade, and then it broke, and I don't know why.
It's probably not your fault.
Yeah. I based my PiHP.js. I made it work by using PyPy.js. There was a talk at PyCon in Australia, I think, by this guy from Mozilla, who built PyPy.js, and it is insane because he's giving slides and he has like real-time code examples, and this real-time code example is like a running Python JavaScript implementation in his HTML slides. And he switches to the next slide and he's like, oh, now this next slide is Python 3 because I just loaded a different JavaScript file. It's pretty insane. And that thing actually works really well.
Thank you.
Also, PyPy.js if you run it in a browser, loads the DOM into Python. So you can interact with DOM as if it was a Python object, even though it's a JavaScript object. And everything works. You can change like the background color of your slide by calling a Python function. It's pretty insane. Completely useless as well. Any more questions?
This will be the last one.
Also, by the way, if you have, it's me spinning. If you have any questions, you can also tweet me. It's probably the best way, or email me.
Hi, I'm wondering if it would be suitable if you use RPython just for parsing, because I'm thinking of building if I'm just like building a parser, would it be suitable to use RPython, or would it be an overkill? For parsing, maybe parse HTML to an AST, or maybe like a restructured text or something else.
Yeah, you could do it.
Yeah,
It's definitely going to be much faster than Python.
Yeah.
like insanely faster.
And would it be possible to like integrate it into another as a library into maybe C or other language?
Yes, like yes and no. So yes, yes, you can make RPython like the C generates. You don't have to compile it. You can have it as C code, and then you can load it into, of course, and load it and link it to any C program you want. The problem is most of it is undocumented, so good luck trying to figure out how it works. It's definitely possible. Like, yes, you can load RPython into a C scope. I just don't know how you should do it. And it's probably going to be not worth the effort.
Okay, thank you very much.
Yeah. Because there's a lot of fast parsers in C already. So maybe you should, like, if you need it in a C, maybe you should do that instead.
Because I don't like the C parser because they're all like something else, and I'm planning to build one of my own, but I don't want to directly.
Yeah. The name escapes now, but like there's a few good C parsers. I don't remember anymore. Because of it, like another lesson I learned, a very difficult task in writing interpreters is writing an interpreter which gives usable error messages. So even when I'm writing my parser, how can I make my parser give an error message which actually makes sense? And that's very difficult. Like parsing takes 1% of effort. Generating error codes is 99% of effort because it's really difficult and you have to track source code lines and figure out what it meant. And I think, yes, we're upsetting the order.
Thank you so much, Joey, for your
thank
great
you.
talk.
Yeah, if you have any more questions, like just find me here or like tweet me and we can discuss all of this. Thank you very much.